Recall that in Galilean transformations, if we want to find the velocity vector of x, y, we perform the calculation, the vector addition of the velocity vector of xc plus the velocity vector of zy. Now, this concept applies to calculating velocities of mechanical waves. So, for example, the sound, which is a mechanical wave. So let's say we have a room that is going to the right, and we have air filled in the room, and we have two people here, and then we have an observer here. So the two people inside the room are going to say that the velocity of the sound is the same in all directions. Now the person is going to say when the velocity of sound going to the right is the velocity of sound plus the velocity of the room, and to the left is going to be the velocity of sound minus the velocity of the room. So that's Galilean transformations applied. Now the question is, does this apply to electromagnetic waves? Let's say, for example, the light. Well, let's say we have the room, we have two light sources, and we have an observer outside the room. The room is going to the right, and these two light sources are emitting light rays. So, and the room is filled with ether, but we need to consider that the ether fills all space, so it doesn't have like barriers. So actually saying that it's inside the room for the question of the having the medium and the sources, it doesn't make too much sense. So now the medium is out of the page, is out of the picture, and we can only consider the sources. So the sources and the observer outside are going to say that the speed of light is the same, let's say 186 miles per second. So this means that the speed of light is independent of the motion of the source.